Hi, good day to you and welcome to my channel where I tutor you in science for free. The topic in this video will be chemical calculations. This video will be a little bit different in the sense that if you see in the textbook, the content page states 3 different chapters to handle such calculations. I will be combining all of these into one. So it may get a little bit taxing, but the good thing about YouTube is you can just pause and you can come back later. Okay, so let's begin. Okay, so first we talk about writing chemical equations. So first, like a mathematical equation, things are written from the left to the right over here, and the reactants that will be mixed together to react are on the left side, and the things that are being produced, the products, will be on the right side. So you can see over here common elements, common notation, subscripts, coefficients are all covered in the previous video. And the interesting thing to note is things like the G, the L, the AQ, or even the S. These are called the state symbols. And state symbols tell the reader what state the substance is at. So if it is in the S state, it's called the solid state. L, liquid, and G, gas. And this funky one, the AQ, will be called aqueous, which means it's dissolved in water. Chemical equations, bottom line up front will be, it has to be balanced. The left side has to be balanced with the right side. And what do I mean by that? All the atoms, all the elements that happen in whatever quantity on the left side should also appear on the right side. And there's no good way actually to think about how to teach or communicate this. Most importantly is a matter of trial and error, and it gets easier the more you practice it. It's like teaching somebody how to generate a thought. You cannot imbue that skill set into somebody. But what I noticed in my years of teaching is usually students who play lots of games and puzzles, be it cards, board games, especially those problem-solving ones, will tend to find this a little bit easier. So looking at a very simple example like this one, you can see that H2 plus O2 equals to H2O. Alright, you can see that the H2 is already balanced, however, the O2 is not. So there's 2 over here, and there is only 1 oxygen on the right side. And in balancing of equations, you can increase or decrease the coefficient until all the atoms and elements are balanced. So over here, the right hand side has only 1 oxygen. I need to increase it to 2 to make the number of oxygen equal. So I put a 2 in front. However, there are now 4 hydrogen atoms on the right hand side, and I only have 2 on the left. So perhaps I can multiply by 2 over here. And now, one final check. The hydrogen is 4 on both sides. Oxygen is 2 on both sides, and ta-da, we are done. And a balanced equation speaks for itself. If it's balanced, you can see it. If it's not, then further work has to be done. So looking at this equation here, chlorine, there's 2 over here and 1 over here. Maybe let's multiply this by 2. Remember, the goal of balancing equations is to make both sides equal, the number of atoms and elements. And the way to do it is to change or alter the coefficient. So let's increase this by 2. And now I have 2 sodium, but over there I only have 1. So maybe let's add another one. One final check. Yes, 2 sodium, 2 chlorine. Okay, let's try this. 3 copper. Maybe let's add a 3 down here. 3 oxygen. I added 3 down here. And 1. Okay, final check. 3 copper, 3 oxygen, 2 nitrogen. Yes. And 6 hydrogen. Yes. Okay, and this is balanced. Let's try this one. So sometimes it appears as a word equation, and you must be able to churn out the symbol and balance it on your own. This is a little bit higher level. In later chapters like salts, like metals, if you have cleared that, an additional one, you have to predict what is the products or even the reactants, and you have to write out the whole word equation, convert it to symbols and balance it out yourself. A little bit more complicated than that, but it's not going to be covered here. We will get to that skill set when it's taught in that chapter. Okay, next will be Ionic equation. Ionic equation sounds very scary. It's actually not, and it's quite straightforward. Ionic equation, the definition is to show that the ions that take part in the reaction leaves out the spectator ions that do not react, and it sounds very bombastic, but the method by which we do it is actually quite simple. Whenever you see a solid, liquid, or gas, you do not split them. You only split the aqueous one. So what do I mean by that. So let's take a look at this. Silver nitrate plus sodium chloride gives you silver chloride and sodium nitrate. So there are 3 AQs over here. Split them. Do not split the solid, liquid and gas. These S, L and Gs, don't split them. Only split the AQ. So bam, you can see that this equation is a very long one. Now, what you see on the left side, you cancel on the right side. Nice, so nitrate aqueous over here on the left side, right side, cancel. Sodium aqueous, left side, right side, cancel. And whatever you have left will just be the product and reactants that you need to write your ionic equation. Ta-da! That's it. This is your ionic equation. So, talking about that is something you can actually predict beforehand. Since solid, liquid and gas, you do not split them. You can zoom in your view straight into the solid, liquid or gas to identify what is actually going on. So for example, this one, you can look at this equation, sodium carbonate, blah, 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 blah. I zoom in straight to the carbon dioxide and water, and I look back at the previous one and I guess where it comes from. So I probably need a carbonate ion, I probably need some hydrogen ions, and bam, that's it. The charges should also be equal. So over here, there's a -2 and +2, and over here will be 0. And on the left-hand side, it is also 0. HCl plus NaOH, hydrochloric acid plus sodium hydroxide. Bam, you get this. So L, you don't split them. So looking at H2O, I probably need a H plus and an OH minus over here. And bam, that's it. There you go. And revealing the whole process will look like that. And that's about it for this chapter. Just pretty straightforward. A lot of balancing of equations. It's actually pretty hard to tell you how to actually go about doing. There's no step-by-step. There's no formula to do this. You have to ask yourself whether is it balanced. If it's not balanced, then you have to do something about it. Yeah, really, I cannot further stress how can you actually do this. Okay, next we'll go on to the mole. This is a word that probably strikes fear in a lot of chemistry students first learning this. The word mole is just a special vocabulary to represent a number. So for example, a pair represents the number 2 and the word dozen represents the number 12. So let's run through a simple exercise. How many pairs are there in 5? So what do? You take 5, divide by 2. You have 2.5 pairs, right? What about maybe 24? How many dozens are there? What do? You take 24, divide by 12. You get 2 dozens, right? That's actually pretty simple and neat. Okay, however, the word mole follows the Avogadro's constant or Avogadro's number of actually 6.02 times 10 to the power of 23. So it's in secondary school level, you can just take it as 6 times 10 to the power of 23. So it's easy to remember. You can just look at it like 6 equals to 1 plus 2 plus 3. Okay, so because atoms are so small, you need a large number like this to significantly to quantify an amount of substance. Okay, so let's say if you have 0.5 mole of iron, you're going to have 3 times 10 to the power of 23 atoms of iron in this example. So don't have to be too caught up by the large number. It's just let it be X. Okay, if you are afraid of it or confused by it, then you sub it in later. Okay, mole, M-O-L-E. The unit, you can use MOL in your working. Okay, and why in this subject this number is of concern? Because 1 mole of a proton or a neutron with mass number of 1 gives us 1 gram. That makes the calculation of the resulting mass a lot easier for us. So the very technical and very correct way of describing it is the relative atomic mass, AR, R for relative, A for atomic, of an atom is the average mass of one atom comparing to 1/12 of a carbon-12 atom. So what does this whole sentence mean? It just means 1 proton. And why using carbon? Probably because carbon is the most stable compound forming element in nature. That's why nature chose it to create living things. Most of living things are made out of carbon. So in simple language, the relative atomic mass is just its mass number. The large number you see in the periodic table in every of this tile, right? So if you think about it, 1 proton or 1 neutron has a mass number 1. It is 1/12 of 1 carbon-12 atom. So this is how it works. In simple terms, just look at large number of periodic table. That's about it. MR is the cousin of the AR, which is relative molecular mass. It has the same definition, the average mass of one molecule of the compound compared to the 1/12 of the mass of a carbon-12 atom. So it's the same, it's just saying, telling you to go to the periodic table and look at the big number and add them all up. That's about it. So for example, in water, so it's like 16 for oxygen and +1+1. For 2 hydrogens, that will give you 18. Things like that. That is pretty straightforward. Like 2 chlorine, so it's 2 times 3, 2 times 35.5 will give you 71. If nitrogen dioxide will be this, will be this. 1 ethanol will be this. Look at all the large numbers, add them all up, you will get this. Yeah, so it's just like that. It's pretty simple and straightforward. And so calculating all of this, you can tell yourself that, 1 mole of chlorine will give me 71 grams. 1 mole of nitrogen dioxide gives me 46 grams. 1 mole of ethanol weighs also 46 grams. So which concludes and brings us to the point, the number of moles in a substance equals to mass over molar mass. And this is a formula that you need to know as a chemistry student. Okay, let's look at the example. Determine the number of moles of an ion in a 196 gram of iron. And how I like to teach, probably in chemistry there's less equations than that in physics. How I teach physics, I just like to tell my students to do this step called extraction. If you see it, a question that requires some calculation of you, a formula, while you're reading, circle it and draw the symbol. You see the mass, you circle it, and you see the molar mass, you circle it and draw the symbol. And whatever the case is, always throw formula first. Number of mole equals to mass over molar mass. And you sub in everything, you will get your answer, given that you calculate them correctly. And equations like this does ring a bell back to earlier school days where you learn distance, speed and time. So it's the same. You can draw a triangle out of it actually, but usually I don't tell my students to do that. You can just remember one statement and one statement only. If it asks for mass and it gives you moles and molar mass, you can write the same equation out and rearrange them later. It's okay. It's not wrong to do that. What is the mass of this amount of atoms of lead? So what is the mass? It's the circle, mass, atoms, this is the amount of moles of lead. And then molar mass, usually questions don't give you. You have to go and look it up yourself. So formula first, throw formula first out. This is what you have. And don't be too confused or thrown off by these large numbers. You can just divide it, put it in brackets, let your calculator do the work for you, punch it in correctly, and you will get your answer. Okay, next we go on to gases. And in gases, it's a little bit different in a sense that they hang around they occupy a large volume because they are gases. So you can see that, in a balloon, it occupies a large space, but the amount of mass inside is actually very little. And the interesting thing is that they operate by particles, the number of particles present. So let's say there are 10 particles of this gas versus 10 particles of that gas, they are going to occupy the same volume in the same given pressure and temperature. So that's why in questions that involve gas, they will always state room temperature and pressure. Gases are very sensitive to pressure and temperature. They change their volume drastically. To keep things constant, usually things are in room temperature and pressure, RTP. And the interesting thing is, 1 mole of any gas occupies 24 dm³ at room temperature and pressure, called the molar volume of a gas. And what is dm³? dm stands for decimeter. Decimeter is 10 cm, so a decimeter cube will be 1000 cm³, because 10 times 10 times 10 will give you 1000 cm³. And 1 mole of any gas occupies 24 dm³, which means 24,000 cm³. And more often than not, questions that involve gases will be in dm³ unit, not the cm³ unit. Okay, next topic, we go on to concentration. Usually there are 2 versions, gram per dm³ and mole per dm³. And over here, it's like what I say, the formula is already staring straight at you. What do I mean? If it is gram per dm³, the concentration equals to the mass, the gram, divided by the volume, the dm³. Or if it is mole, so it's like the number of mole, concentration is equals to number of mole divided by the volume. Okay, we jump into some examples. So over here, 120 milligram of paracetamol in 5 cm³ of solution. In this unit, concentration, gram per dm³, So how do we do it? So first we convert over. The volume is dm cube, concentration will be the gram, convert milligram to gram will be this, and then you just divide it, you get this answer. 3.5 gram of sodium hydroxide in 100 cm cube of water. The number of mole equals mass over molar mass, which is this. Then the concentration will be number of mole over the volume will be this. Punch everything into the calculator and you will get this. So one interesting maneuver you can do, if you see gram per dm cube and you want to convert it to mole per dm cube, you can multiply it this way. You can convert it by using this formula. So in an example of 73 gram per dm cube hydrochloric acid, how many moles of HCl are there in 250 cm cube of this acid? First convert, you get 2 mole per dm cube, then you multiply by the required amount of volume. 250 cm cube is 1/4 of a dm cube. Okay, so hope those information was not too heavy. You'll get a grasp of it if you handle more equations. The feedback is very important, so this is practically math. And to handle math comfortably, more experience have to be done. You have to put in the hours put in the required hours. Okay, coming together all this information, we will talk about chemical calculations. So let's look at this. You have this equation, mass of solid to be determined, 16.8 gram of sodium hydrogen carbonate to begin with. So in questions like this, usually we are more concerned about, it's always prudent to find out the number of moles that are participating in the reaction. So over here, number of moles of this is, first throw formula, number of moles of this equals mass over molar mass. You'll get this. Then because there is 1 mole, 0.1 mole of this, and because there's 0.1 mole of this, you throw back your formula, number of mole equals mass over molar mass. You will dump in all the numbers and bam, you will get the answer. Let's talk about gases. Having this equation, calculate what volume of nitrogen reacts with 60 cm cube of hydrogen. And remember that gases, they react by their volume is controlled by the number of particles inside. So if 3 units represents 60 cm cube, 1 unit represents 20 cm cube, right? That's the answer. Okay, next example of gases, you have this equation. Calculate volume of carbon dioxide formed when 3 dm cube of butane burns completely in oxygen, excess oxygen. So whenever we see this word excess, just know that the other party is completely used up. Oxygen is not used up, the other party is completely used up. So you don't want to know that butane is completely used up. I usually draw this bar graph on my students' papers to tell them how to mentally understand this. This is what it means by excess. Okay, next, 3 dm cube of butane. 2 unit represents 3, 1 unit represents 1.5 times 8 will give you 12. So those are some introductory questions involving mole and gases. Next, we talk about limiting reactants. So limiting reactants is, let's say for example, you have a shop that sells pens. You need a pen and a pen cap to be considered a complete product. If you have 8 pen cap and 10 pens, how many pens can you sell? You can actually only sell 8 because the pen caps are in this case, is the limiting reagent. It gets completely used up and there's no more to react. So let's look at a simple example. This equation, 13 grams of this, 8 grams of this. Who is the limiting reactant? So bam, bam. Therefore, the limiting reactant will be zinc because zinc is lesser because it's 1:1, and the excess will be this amount of mole of sulfur. You convert it back to mass will be this amount. And finally, we go on to volumetric analysis. Mainly, this talks about titration, and titration is a bombastic word just to describe trial and error in terms of finding how much volume is needed to neutralize something else completely. Okay, so of course in science, a certain factor must be known and a certain factor must be unknown. So you take the known one and you put it into the burette, and the unknown concentration you put it into the pipette, into a conical flask with a certain amount of indicator. And of course, this video will be focused more on the calculations part of it. This is just an overview. You will get your chance when you enter the lab in your school. Then set it up accordingly using the retort stand to clamp the burette and release the titrant slowly, drip by drip, and swirl after each drip until there is a noticeable color change. Then the reaction is complete. You may then record the amount of titrant that has been released. Remember in first chemistry video, the burette is to release accurate amounts of liquid. Pipette is to pick up accurate amounts of liquid. So let's go into the main part of this. This equation, this amount of ammonia required this amount of sulfuric acid for endpoint titration. Calculate the concentration of the ammonia. This is how you will be doing it. First, calculate number of mole of this. Because there's more information given on sulfuric acid, you get this amount of mole, and by equation there's 2 reacting with 1, therefore you get 2 of this. This is the number of mole for ammonia, and check back, this will be therefore the number of mole for the number of mole per dm cube for ammonia. Finally convert, you'll get your gram per dm cube. So you can see from the start of this video to this point, there are certain skill sets that will be brought along progressively, writing balance equations, formulas, calculating, things like that. So if you are not sure, this is confusing, you can always write them down together under the reactant. Let's look at this example. This equation, this concentration, and this amount of mole. So find the number of mole of copper sulfate required, then dump it back into the volume, and you will get your answer. And that is all for today. Hope you enjoyed this video. Do give it a like and subscribe, and share it with somebody who needs to see this. And I will catch you in the next video. Bye!